prior to software comes hardware on which the software runs. And prior to algebra comes arithmetic. So the first topic which we'll consider is implementing arithmetic operations in the world of Boolean circuits. That is the mathematical model for computer hardware. So let's first talk about the mathematical model of the hardware that we have. Our hardware works with zeros and ones. Everything is binary in the computer at low level. And we have mathematical Boolean things to work with these zeros and ones, true and false, well, with binary values. And we'll define the circuit as a model of how we wire together elements that are able to compute very basic Boolean operations into something reasonably large. So as soon as we are talking about wiring things together, linking things, of course, naturally graph model arises. And so it's not coincidence that a circuit is a directed acyclic graph, which is labeled. So the graph itself signifies the links between the elements, and the labels on these graph nodes signify like what elements we place in what nodes and what inputs and outputs our circuit has. Before building a circuit, we need to agree upon what base we are using. So what is the set of elements that we are actually able to employ? And we'll use throughout our course the basic set of conjunction, disjunction, and negation. And conjunction and disjunction will be binary with two inputs. So our base set of Boolean joins, of Boolean operations, is two input disjunction, two input conjunction, and single input negation. As soon as we agreed upon the base that we use, we now can define a circuit as a directed acyclic graph. So we have nodes, we have arcs, directed edges between these nodes. And this graph is acyclic, so we are not going to find any cycle of this form, so that we start at some vertex, we go along the arcs, and then we get back to the same vertex. So if we respect the arc directions, we cannot get back to the same vertex. So for instance, in this circuit, this guy is not considered to be a cycle, because if we observe the directions of the arcs, we cannot, make the full loop here. Now we need to label our nodes, and the nodes are labeled with three types of labels. So every node is labeled as either an input node of a circuit or a gate node. So we have inputs and we have gates. Gates are the actual Boolean operations that we have. So for instance, if we say place disjunction here and conjunction here, now these are two gates of our circuit. For each gate, of course, the number of input arcs should correspond to the number of operands for these Boolean operations. So if we are dealing with binary disjunction and conjunction, each node that is labeled with this type of Boolean operation should have exactly two incoming arcs. And if a node has no incoming arcs, it can be called an input node, and it is usually labeled with a variable. Usually variables are denoted by, say, xi or x, y, z, etc. So here we have a circuit in which each node is labeled with either a variable or a gate, so a Boolean operation. And also, besides every node being labeled as one of these two types, some of the nodes might also be labeled as outputs. So actually, any node and any combination of nodes can be labeled as outputs. Even input node can be labeled as an output node. So for instance, if this node is labeled as output, say F1, and this node is labeled also as an output, then we have two outputs in our circuit, the first output, if we treat this output as a Boolean function of the inputs of the circuit, is just equal to x1. This is, by the way, is called a projection function because it takes a tuple of values and it outputs only one component of this tuple. So it kind of projects a tuple of values on one of the coordinates. And f2, the output f2, is also a function of two variables, is computed in this output at this node. And this is a conjunction. So it's a conjunction of two things. The first thing that comes to this conjunction is x2. And the second thing that comes to conjunction is the result of disjunction of x1 and x2. So this circuit has two outputs. Okay, so as soon as we define what a circuit is, what a Boolean circuit is, let's now answer two questions. How can we build any circuit for a given function? For, well, if we need to have some given functionality, how we implement it in this model. And then as soon as we solve this problem of existence, we can then come to a problem of efficiency. So how do we distinguish which circuits are good or bad, efficient or inefficient? So this is what we'll now talk about. So let's first talk about existence. All right. So we see that we can compute function with a circuit and immediately build a formula just by looking at this circuit and processing this graph from bottom to top. The fact that it's an acyclic graph allows us to order its vertices. So as soon as we see some output node, we see what preliminary values we need to be able to compute the result at the output node. And we can inductively proceed to computation of these values and so on and so forth. Eventually, we actually are able to write down a formula for this output, how it is determined by the inputs of the circuit. And we can proceed vice versa. So whatever function we are given, so suppose that we have a different function, say XOR, one of the standard functions that we'll need. Suppose that we have two variables, xy, and we have XOR function of x and y, we'll denote it by this plus in the circle plus, and the XOR function is defined, as you might remember, like this. So the truth table, the table that lists all the values of a function for all the input tuples, is 0, 1, 1, and 0. So whenever our input values differ, our function outputs 1. As soon as they are equal, our function outputs 0. So this is XOR function. Now, how do we build a circuit for this function? Now, we may first want to try to build a formula for it. So let's do this. So we can take any tuple of values on which our function is equal to 1, and we can construct a conjunction which is equal to 1 on just this tuple of values. So a conjunction whose truth table looks like this: 0, 1, 0, 0. And what does this conjunction look like? Conjunction of just the variables that we have. If we take x with negation and y without negation, we actually get the desired truth table of such conjunction. This thing is called an elementary conjunction, so a conjunction of variables and their negations. And not to mistake between these two different symbols, disjunction and conjunction, I think we better just skip this symbol altogether, just as we skip the symbol of multiplication. And actually, conjunction of two variables is indistinguishable from product of these two variables in the world of Boolean algebra, where we just have zeros and ones. Okay, so here we have a term that behaves like this. And now let's take a different tuple on which our function is equal to 1 and try to build an elementary conjunction that looks like this. Looks like 0, 0, 1, and 0. So it gets value 1 on exactly this tuple, and everywhere else it gets zeros. So such elementary conjunction can look like x and negation of y. And now to be able to construct the truth vector of our function from the two given truth vectors of these elementary conjunctions, we can just merge them using disjunction operation. And this is the general idea that underlies the canonical DNF expansion for any Boolean function. So we'll get back to this in a few moments. For now, we see that we can express our XOR function for two variables using just conjunction, disjunction, and negation, our standard base that we agreed upon using. And now, as soon as we have a formula, we'll look at the last operation, which is to be carried out when we compute this formula, and this is disjunction. So we just create a disjunction node in our circuit, and this disjunction should be supplied with the result of two conjunctions. So that's we have to compute these conjunctions. And also, I will sometimes denote conjunctions as ampersands. So now the first conjunction needs to get negation of x and y. So let's now introduce the input nodes x and y and compute negation of x so that we're able to use it in this conjunction together with y. And the second conjunction is symmetric, so it needs the negation of y and x. So our circuit built by this formula looks like this. Okay, so we can naturally use formulas to build circuits, and thus for any function we can first build a formula and then construct a circuit. And already here we can have different formulas for same functions. For instance, we can take the same XOR function, which is computed by the formula not x times y or x not y, and use a different formula for the same function, a formula which is xy negated times x or y. So we can see that this formula works because for our function to be equal to 1, we should have at least one of the two variables equal to 1. On the other hand, we have to have not both of the variables equal to 1. And we see that if we compute a circuit using this formula, we get a slightly different circuit. So let's see what this circuit would look like. We have a conjunction, and to this conjunction we supply the results of negation of another conjunction, so like this, negation of conjunction of x and y, and the other thing would be the disjunction of x and y. So we have two inputs again, x, y, and we have to compute conjunction of x and y, then negate it. We'll have to compute disjunction of x and y, and then conjunction of these two guys. So in both circuits, the output is this last node, and here we have implemented this XOR function in the output. But these circuits are clearly different because they have different number of operations, right? The left circuit has 5 gates and 2 input nodes. The other circuit has just 4 gates. So in some sense, we can say that this circuit is more efficient than the left one. And this is called the size of the circuit. So the number of gates is the size parameter is just the number of gates. The input nodes are not counted towards the size of the circuit, just the number of Boolean operations. Okay, so what other efficiency measures we can have for a circuit. We can track the time which the circuits might need to compute the answer. So if we assume that each Boolean operation, each gate that we have in our circuit, needs one moment of time, like 1 second, 1 unit of time, to compute its result, given that it's applied immediately with the inputs, our circuits actually take some time to compute the output. So for instance, if we look at the left circuit, before we can compute the value of this node, we first need to supply it with inputs. And these inputs are provided by this layer of conjunctions. So they also need to compute their output based on some input values. And they use, in particular, the results of these two negations. So before the negations compute their results, we cannot compute the result of conjunctions. And before conjunctions compute their results, we cannot compute the final result, which is the output of the circuit. So we need 3 units of time to compute the result here. As well as we need 3 units of time to compute the result here. After the first unit of time, this layer is computed. After the second unit of time, we have this negation computed. And after the third unit of time, we have this result conjunction computed. So how do we mathematically model this amount of time needed to compute the result? Actually, it is defined by the length of the largest path that goes from some input of the circuit to some output gate of the circuit. And this is called the depth of the circuit. So depth is the second main measure of efficiency of the circuit. The size is just the number of gates, and the depth is the length of the longest path from an input of a circuit to an output of a circuit. So we cannot say that the circuit computed all its outputs before this computation along this longest path is finished.